got our EDTA that was heated and then left to cool in a desiccator. And we're going to weigh out about 0.6 grams and write down exactly how much that it is so we'll know the concentration. And it doesn't take very much to get to 0.6 grams. So we're transferring our, in this case, 0.606 grams of EDTA into a 500 milliliter volumetric flask. We're going to add some water and heat it to help it to dissolve. So we're going to do 7.5 grams approximately, but we'll write down exactly what we have. Of our calcium unknown. So these were shells, whoops, that you guys crushed up for us last week for our calcium source, but you could use a variety of different things depending on what you wanted to test. Go this way, sorry. I'm going to call that good enough. So 7.83. So this is best for the instructors to help do. We're measuring out 18 milliliters of concentrated HCl. This is going to help break down that calcium compound and all the other things that are in that shell. So we're carefully adding some acid. Add a little bit of water in first to help solubilize things, make it a little bit easier to work with. Do this very slowly and carefully. A lot of exothermic energy to worry about here. And definitely you do this in the feet. Give it a chance to calm down a little bit before you move on, but still slowly and carefully with adding in water. Continue adding water. After it's calmed down, then you can add water much more quickly. It's a good idea to use a funnel. You're using a volumetric flask. You can also complete this same work with a beaker if you don't have volumetric glassware. It's just not quite as precise. Swirl until it meets those. Continue adding water. Ultimately, our goal is to end up filling this up to the volumetric line of 500 milliliters. But take your time, slowly but surely. This is something that you could prep in advance for the students, or you could have them grind up the shells, and then you could prep this separately so that they have their samples to work with later. And this can be used for both this experiment and the gravimetric analysis experiment. So now we're right at the end, just getting that meniscus right up to that line. Pretty close. So we've got a little bit of bubbles from the foam. We still have some bubbles forming here, so the calcium carbonate is still breaking down. You may need to let this sit for a little bit so that can finish dissolving. So we're adding our EDTA, that's our titrant, into the burette. The stop clock is closed at the bottom. Make sure you do that before you start pouring. And then we're using a beaker to pour, and then also a funnel. And that's going to be the best way to make sure that you don't make a mess. You do want to be careful with the funnel, because once you get up to the top, it does start to fill faster. That is where I've had a lot of students make a mess. And then we're bringing that right up down. The meniscus is pretty close to that 0 line, and that'll be our starting point. For our sample to finish dissolving, we're going to go ahead and run our blank sample, and that's just 50 milliliters of distilled water. And then we're going to add in, I'm going to reach for our indicator. So this is the Eriochrome Black-T, and we need 6 drops. 6. And this is already blue. So that's handy because it's saying that we don't need, our blank is going to be 0. Because our change we're looking for is red to blue. So since we're already starting with the blue, our blank is done. All right, so with tap water, there is calcium and other metals in there that the Eriochrome will bind to, and so we get this really vivid pink color. And this is actually from just a couple of drops. So tap water is another thing that we can't test. So if we do a test with our tap water to find out calcium, we could do this to determine water hardness. So I'm just adding in, there's probably a lot. And we're looking for that pink to blue color change. It'll very briefly be purple in the middle. It's starting to lighten because it's getting more dilute. Yeah, it's running right out. This is a case where a little bit of tap water and then dilute up rather than an entire thing of tap water, because that made it all the way down to the 50. All right, so I'm pouring. This is our pH 10 buffer. The instructions for how to prepare that are in the protocol. You can also buy pH 10 buffer. So we need 3 milliliters of this. Put that up so I can see what I'm doing. This is where the analytical chemist in me comes out. There we go. So it's 3 mils. And then we also need 50 milliliters of distilled water. Right, we're running our blank. So that's all we need for this. Then we're going to add in about 6 drops of the Eriochrome B, although it looks like we could get by, it's still blue with fewer. So I might change that to 3. So this turned blue right away. So that tells us that our blank doesn't have anything extra floating in it that we have to worry about. So we don't need to worry about subtracting a blank in this instance. It's still always a good idea to test this to be sure. Set up a dimensional analysis to calculate our concentration of our EDTA solution. So molarity, if we're looking at this in terms of doing a reaction, molarity is going to be the better, more useful way to go. So we needed our formula mass for EDTA. That's provided in the handout. EDTA, remember, is not just the compound itself, but it's also a hydrated compound, and it's got a sodium counter ion. So that's where this big mass is coming from. So we knew we had 0.606 grams of EDTA. And we also knew that we had dissolved that into 500 milliliters for our solution. And so I'm starting off, we're converting our grams into moles. So I need to divide by my formula mass, that's that 372.24 grams, and that lets us convert into moles. We can cancel our grams. Now we've got moles of EDTA per milliliter. And so now we need to convert our milliliters into liters. So since our milliliters are in the denominator, we're going to have our milliliters up in the numerator for this step. That's going to let us cancel milliliters. There's 1,000 milliliters in a liter. So now our units are moles per liter. So everything on the top we multiply, everything on the bottom we're going to divide. And when we do that, we end up getting 0.00326 moles per liter, or you could also write 0.00326 molar, capital M. We also went ahead and did the same calculation, but for milligrams per milliliter. It's a shorter calculation. So in this case, again, we've got our grams per milliliter, so 0.606 divided by 500. And in this case, we're already in milliliters, so we just need to change our grams into milligrams. So 1 gram in the denominator lets us cancel out our grams, and then our milligrams are in the numerator. That'll leave us with milligrams per milliliter. Multiply everything on the top, divide everything on the bottom, and we get 1.212 milligrams per milliliter. Our sample, finally. If you end up that it's looking cloudy, you can go ahead and filter it, because there may be binders, especially if you're using a calcium tablet or a plaster sample, and that'll just help pull out any of the extra stuff that's in there. So we got some of that. You actually only need 1 milliliter for this. So a good idea might be that this is for a group or a class, that they maybe all take turns grinding up your sample and then combine it, and then you prep this in advance. And this is enough for 500 samples. So you don't have to do a ton with that. So we need 1 milliliter of our calcium sample, which is not going to be very much. If you have a volumetric pipette, you can use that. If you, want to be more approximate, 20 drops, there we go, is about the same as a milliliter if you have a dropper. So that's my 1 milliliter of sample. It's not very much. We're going to dilute that by adding in 50 milliliters of our distilled or deionized water. Make it easier for things to interact. And then we've got 3 milliliters of buffer to add in, and that's going to bring it to the pH that we want. We want it to be this pH 10 buffer. Going a little overboard. I'm just going to take a little out. Perfect. Okay, let's get that all mixed. And then the last thing we need to add is our Eriochrome B. So as we've been working with this today, we've seen that we actually do not need 6 drops. So I'm just going to do 3, I think. Oh, there's our wine red color. So isn't that beautiful? So give that a swirl, make sure everything's mixed real well. And you can see it really well you've got a white burette stand like this is, or if you don't, a piece of white paper underneath will also help make this more visible. You notice it's really hard to see on the black countertops, but if you put a white background underneath, it's easier to see. And I've also had students use their phones to shine through it, and then that also helps it make it easier to see. All right, so we're going to start titrating. I am right-handed, so I'm actually going to turn this so I can swirl with my right hand, and then we're just going to start adding in some liquid. So our goal is we want to, we're starting to get a little bit of blue showing up here in the middle already. So once that blue starts showing up, I slow way down. Trying not to overshoot. You see it's starting to turn a little more purpley in color. So right now I think we're almost there. So we've made it more to a purple color. See that blue in the middle? Okay, this is a little more purple. It's so pretty. For that moment when it's blue. And once you've done this once, I would keep your final sample, because then you'll have that blue for comparison, and then it's easier to tell when you're done for future samples. This just gets prettier and prettier. I think that might be our blue. Write that down, and we might add a little more just to be sure. So that's 32.50, and we started at the 0, so that means our total volume then is 32.50 milliliters for that sample. We did our blank to begin to correct if we needed to for water. That also was 0.0. So our final volume then is 32.50. There's the blue. All right, this is going through some of our questions on the results and discussion. So the first question we have is we wanted to find the concentration of calcium ions in our solution. So the first thing we needed to do was get from the milliliters of EDTA to moles or grams of calcium. So we had a couple things we needed to bring in to help us with this calculation. One is that we know that the concentration of EDTA, because you did this earlier, is 0.00326 molar. And then the other thing we needed to know is that when we look at the reaction in the description of the protocol, it's a 1 mole of EDTA reaction is going to go with 1 mole of calcium ions. So it's a 1-to-1 mole ratio. So if we start off with our 32.50 milliliters of EDTA solution, we need to change milliliters to liters. So we'll divide by 1,000 milliliters, change that to 1 liter of our EDTA solution. Milliliters cancels. So now we're to liters, and we know that molarity is the same thing as moles per liter. So that tells us that we can divide by 1 liter, and that's equivalent to 0.00326 moles of EDTA. So that's going to let us cancel our liters of EDTA. Now we're to moles of EDTA, and then because this is a 1-to-1 mole ratio, we divide by 1 mole of EDTA, and that's equivalent to 1 mole of calcium ions. Moles EDTA cancels, we're left with just moles of calcium ions. This is equal to then everything on the top is multiplied, everything on the bottom is divided, gives us 0.000-10595 moles of calcium ions. You can round if you're thinking about sig figs. I would hold on to these until later because we're going to use this for further calculations. The next step we can do is we can take our moles of calcium ions into a molarity. So we know that we used 1 milliliter of our calcium solution, and in that 1 milliliter there was this 0.0010595 moles of calcium, because that's what we just calculated. So if here I've already got my moles, I just need to convert my milliliters into liters. So I'm gonna, since this is in the denominator, that means that the milliliters needs to go in the numerator for this conversion, and we're gonna divide by 1 liter. Milliliters will cancel. So now we've got moles per liter, and that ends up being 0.10595 moles per liter of calcium ions. The other thing we could do is also calculate this in milligrams per milliliter. So we've got our moles, the same value we started with. We've got our 1 milliliter in the denominator, and I need to change my moles into grams. So I've got 1 mole of calcium is equal to, if I go to the periodic table, 40.08 grams of calcium. So that's going to let us cancel our moles and change into grams. So now we're in grams per milliliter, and if we take it one more step, I'm going to divide by grams. 1 gram, there's 1,000 milligrams in a gram, so this will give us milligrams per milliliter, and that ends up being 4.238 milligrams per milliliter of calcium in the solution that we prepared. Okay, so question number 2 in the post-lab had us thinking about how many grams of calcium ions then we had in our total solution. And then question number 3 is, if you have a solid sample, how many grams of calcium then are in that? Our solid sample we put entirely into our solution. So we had 7.836 grams of seashell that we dissolved into 500 milliliters. And we only used 1 milliliter of that. So what we're trying to figure out then is, in that 500 milliliters, how many grams of calcium total do we have? So starting with that 500 milliliters, we're going to convert that. To make our lives a little easier, we went ahead and used the milligrams per milliliter value that we just calculated in 1C. You also could start with your molarity for this part and then convert into grams if you'd prefer. So here though, since we have that value, we divided by the 1 milliliter, and then that we've got 4.238 milligrams of calcium for every 1 milliliter. That lets us cancel our milliliters. We're left with milligrams. And since we're interested in grams, we're dividing by 1,000 for the milligrams and changing it to 1 gram. So the milligrams cancel 1 gram of calcium ions, multiply everything on the top, divide everything on the bottom, and that leaves us with 2.119 grams of calcium. This is both in that 500 milliliter solution and in the shells that we weighed out. So that's how many grams we have. And then question number 4 has us thinking about then what percentage of our shell sample is made up of that calcium. So for a percent, right, it's your part divided by the whole times 100. So our part we're interested in is the calcium, so that's 2.119 grams of calcium ions. We're dividing by our entire mass of shell, so 7.836 grams of the shell times 100, and that ended up giving us 27.1%. Those of you teaching chemistry, this could be a good chance to think about masses, and so if this is all calcium carbonate coming from your shell, what percentage of that shell mass should be calcium versus what percentage should be carbonate? And then they could compare their results to what you found here with these calculations.